Hi everybody, welcome back to the channel. In this video we're going to take a look at a couple of examples using exponential functions and what we saw in the last video, which was talking about solving a differential equation. One specific type of differential equation that gives us a solution or a function of y that is e to the kx or kt. In fact, you actually have a constant thrown in there as well in front as a y of 0. So let's go ahead and jump in. We're going to take a look at two examples. The first one is going to involve population growth, and the second one is going to involve something called Newton's law of cooling. Okay, so let's go ahead and start reading. This problem says, use the fact that the world population was 2,560 million in 1950 and 3,040 million in 1960. Okay, by the way, I don't know why they're using thousands of millions like that. That just means 2.56 billion with a B and 3.04 billion with a B. So we know the population in 1950, we know the population in 1960, and it says use that fact to model the population of the world in the second half of the 20th century. And then there's actually a really important sentence in here, even though it's in parentheses. I'm going to go ahead and underline this. It says assume that the growth rate is proportional to the population size. So here's the thing, we tend to think this way. We tend to think that I'm going to use kind of a constant growth rate there. But unless we're told that, we really don't know that. And so here's what that means in our math notation. The growth rate, you should think about derivative. So what that sentence is saying is that assume that y prime is proportional. That should kind of stand out from the last video. In the last video, I called it directly proportional. So it's proportional to the population size. So that means that k times y is equal to y prime. Okay, and this is actually really important for us because we know what y is then. If you remember from the last video, if we have this equation that y prime is equal to k times y, we know exactly what y looks like. Y looks like y of 0 times e to the kx, or I tell you what, since we're using time here, why don't we use t as our input variable instead? But y is equal to y of 0, so this is kind of like your initial population. Okay, in the last video we called that our y-intercept. This is like our initial population here. And then the question is, what is our relative growth rate? One way to think about the relative growth rate is to talk about what k is. Okay, and then it also says use the model to estimate the world population in 1993 and to predict the population in the year 2020. Well, by the way, I don't know when this book was written or when this problem was written, but now it's the year 2020. So you could actually go and look up online what our current world population is and see if this model actually got us close to what we were trying to have or what we thought we would have. Okay, so here's the deal. When we have this statement in parentheses, we're assuming the growth rate is proportional to the population size. We get this equation. When we have that equation, we know what y looks like. Now we can go ahead and think about the initial population, and it doesn't tell us where to start, but it seems pretty natural in this problem to kind of think about using 1950 as maybe a starting point. So when we talk about initial population, we're going to use t equals 0. I would say let's go ahead and use the year 1950 as our starting point for that. So that means that y equals let's see, in 1950, the population was 2,560 million, and then e to the kt. And even though I don't love this kind of idea of using thousands in here, we'll be consistent with what the problem says. So we'll go ahead and just use 2,560. Just keep in mind that that's talking about millions of people. Is what that number represents. Okay, so I'll tell you what, now at this point, it is really not a calculus problem. Okay, we've kind of done the calculus part. So a lot of the problems that we're going to see in this section, a lot of the work feels like algebra, feels like some stuff you've seen in a past class dealing with exponential equations and solving an exponential equation using logarithms. Okay, so the calculus part comes in from knowing that the growth rate is proportional to the population size, which gets you these two equations here. But now, at this point, it's really not any calculus. Okay, it asks us, or we need to use what information we're told. We're also told that in the year 1960, which is 10 years later, so we're going to go ahead and use 10 years after 1950 here. We'll go ahead and plug in 10 for t, e to the 10 times k, and we know that in the year 1960, the population is 3040. It's 30, 40. So we get something like that. And now there's no calculus involved. Go ahead and divide both sides by 25, 60. So 30, 40 divided by 25, 60 is equal to e to the 10k. You probably remember how to deal with something like this. Take the natural log of both sides. When you take the natural log of e to the 10k drops down in front, and the natural log of e is just 1. So in other words, you get something like 10k equals the natural log of 30, 40 divided by 25, 60. And then go ahead and divide both sides by 10. So k is the natural log of 30, 40 divided by 25, 60, all divided by 10. Now, by the way, word of caution, this is just a common mistake I see from a lot of students. If you're going to use your calculator for this kind of a problem, which is fine to plug this in, a lot of people forget to close this parenthesis in your calculator here. It does make a really big difference that this 10 here is outside or underneath the logarithm. It's not inside of the log. It does make a really big difference, so just make sure you close that parenthesis. Okay. Now, you should get some kind of a decimal here for k. Let's see, I think if you plug this in correctly, you should get something like 0.017 or something like that. You can carry that decimal further and have more decimal places. I would recommend that probably, just so that when you go to answer the question down the road about what the population is in a certain year, you're not getting a little bit of a rounding error in there. So take this decimal really far so that you can get as precise of a value as possible. Okay. Again, really on this right side, no calculus involved. I don't have a ton of space on there, but you get the idea. That's a lot of stuff that you should have seen in past classes. Okay. So let's see, just to finish this out, use this model to estimate the world population in 1993. Let's see, for that we would use 1993 minus 1950 was where we had our starting point. So go ahead and use t equals 43. And then let's see, 2020 for this year. Minus 1950, that's 70 years later. And so you can go ahead and plug that in for t into your function that looks like y equals, let's see, it was 2560 times e to the, you could say k. I'm going to go ahead and just kind of put k as, you could just write it as a decimal but carry it really, really far, or you could just write it as the natural log of 3040 over 2560, and then all divided by 10. If you want to be as precise as possible in there, and then multiply by t and plug in 43 and plug in 70 for your t values and figure out what you get for y. Okay, so again, this part of the problem shouldn't be anything that's new or anything you haven't seen before, but the calculus part is going from the derivative formula to back to that y formula of an exponential that gets you back to some of your college algebra days. Okay. All right, in the next example, we're going to use something that you may not have seen before. We use population growth in the first one. In the second example here, we're going to use something called Newton's law of cooling. And Newton's law of cooling still looks really similar, but there's just one little difference in here. Here's what Newton's law of cooling says. It says that when you change the temperature of an object, and you put that object somewhere into some kind of surroundings, the object either warms up or cools down, and it follows this pattern of change in your temperature. So dt over dt equals k times t minus t subscript s. Okay, this is a set formula for Newton's law of cooling, and here's what this is doing. There's actually a lot of t's going on in here, and so let me just put it this way. So big letter T is talking about the temperature, and little letter t is talking about the time, and then t subscript s over here is talking about the temperature of your surroundings. And so wherever you're moving your object to, what's the temperature around that object now after you've moved it? Okay, by the way, this t subscript s, this is fixed. This is a constant value. This is not something that's changing. So let's go ahead and read the problem up above. All right, so we're starting with a can of soda pop. I'm from Michigan. We call it pop up there. I take a lot of ridicule for that, but that's okay. So we have a bottle of soda pop here is at room temperature, which is 72 degrees. Think about that as being like the initial temperature. Okay, so it's starting at 72 degrees, and that's being placed in a refrigerator where the temperature is 44 degrees. So the temperature of 44 degrees, that's now the temperature of the surroundings. because that's where you put the bottle of soda. All right, so let's keep in mind that 44 degrees goes in for T subscript S, and that's a fixed value. So let's go ahead and see what we can do before we even look at the next sentence. We're told that dt over dt is equal to k times t minus 44. And this capital letter T right here is T with a little lowercase letter t as its input variable. Okay, and what we're going to do here, because of this 44, it actually looks a little different than in the last example. This almost kind of looks like y prime equals k times y, but not quite because of that minus 44 there. So what we're going to do is we're actually going to use a substitution of variables. Let's use this. How about y equals t minus 44? And if y equals t minus 44, the part in the parentheses, go ahead and take a look at y prime. Y prime should just be equal to capital letter T, because the derivative of a constant, minus 44, is just 0. So in other words, go ahead and replace the t minus 44 with a y, and replace the t prime with a y prime. Here's what your new equation should look like. It should look like y prime equals k times y. Well, that should look familiar. That's good. That's what we want, because now we know exactly how y behaves. Y is equal to y of 0 times e to the k t. That's what we just saw in the last video in the lesson. That's kind of the new main idea of the calculus part of these types of problems. So now we have this type of a function right there, and we got to think about what y of 0 is. Okay, remember y of 0 is talking about at the very beginning. Now y of 0 is different than t of 0. Let me go ahead and put this on the next page here. Y equals y of 0 times e raised to the kt, but y of 0 is equal to t of 0 minus 44. Okay, so what was T of 0 again? That was the initial temperature of the soda pop. That was actually 72 degrees. All right, so we can find y of 0 as a constant because we know what the initial temperature was. And so we end up getting an equation y that looks something like this. Let's see, I think that's 28. So y equals 28 e to the k t. And just like in the last problem, this part right here now is where there's really no more calculus involved. Now it's really just algebra, and it's back to your exponential function days. So let's go ahead and use that equation, and we can go ahead and use what information we know or what we've been given and solve for k, and then answer the question that we've been asked. Okay, so if you look back in the problem, the other information that we haven't used yet is it told us that let's see, after a half an hour, the soda pop has cooled to 61 degrees. So we can go ahead and you can either use 1/2 as a half an hour, or you could use t in minutes instead of hours, and you can use 30 minutes. But here's the idea, is that the soda is 61 degrees when you plug in 30 minutes or a half an hour. I'm going to go ahead and use minutes. It doesn't really matter as long as you're consistent. And if you use minutes in one spot, then you got to use minutes in the whole entire problem. Okay. Now, could you go solve for k? Sure you could. That looks like 61 over 28. Then take the natural log of both sides to get rid of that e. This is 30k. And get k all by itself. It should actually look a lot like what we had in the last problem. It's the natural log of 61 over 28, close parentheses, all divided by 30. And then go ahead and plug that back into your original problem. Okay, so now that you know what k is, you can say, oh, okay, my equation looks like y equals, let's see, it was 28 e to the, go ahead and just plug in that k. I'm going to kind of copy and paste and cheat a little bit, times t. And now it's just a problem saying, could you answer the questions? What is the temperature after another half an hour? Plug in t equals 30. Or I guess actually plug in t equals 60 because it's another half an hour later, so 60 minutes after you started. And then how long does it take for the soda to cool to 50 degrees? Plug in 50 degrees for y, solve for t. Again, really no calculus involved at that point. You could solve both of those. Okay. All right, here's a couple examples. I hope you've enjoyed.